Good morning, Dallas. Good afternoon and good evening to all the viewers. And whichever part of the world you are viewing this Friday talk show with your host, Rajiv Kulkarni. Global Electronics brings every Friday a talk show on electronics subject, electronics topic concerning the electronics manufacturing activities globally. So it can be design related, it can be production, it can be process related, it can be market trend, it can be anything that relates to the global electronics manufacturing throughout the global. And last 2 weeks, we have been discussing on one particular topic, which is why is the V model important for Ultra HDI PCB design? Yes, we did part one. We did last week 2.0, and today it is 3.0. Just to give you a little update on that, designing Ultra HDI PCBs presents significant challenges due to their complexity, routing, congestion. High component density and fine features lead to intricate routing challenges. And there are a lot of challenges like signal integrity, fine tracers. We talk about PCBs all the time, about the fine tracers and so on and so forth. So in order to discuss the point 3.0 of V model importance in Ultra HDI design, we have Mr. Ambaprasad, who resides in Silicon Valley of India, Bangalore city in Karnataka state in the southern part of India. So Ambaprasad carries a rich wealth of experience in the design sector in the industry for the last more than 4 decades. And he has been serving the electronics industry in various capacities. And also he is the current president of Surface Mount Technology Association of India, that is SMTA of India. Let's welcome Mr. Ambaprasad this evening. Good evening, Mr. Ambaprasad. How are you this evening?
Yeah, almost doing good.
Doing good. So weekend, ready for the weekend?
Yeah, next week I have a training session to conduct.
Okay, great.
So
Anyway, then definitely you are ready for the weekend. So have some break between the next busy week and the week which is just over. So Ambaprasad, let's begin. I will share the screen. So let's start, beginning our presentation slide, and then we
can
take
go
it
to
from
page
there.
30.
Page 30 of whatever the information you have shared. So many pages here. Give me 1 second.
Yeah.
Oops. I'm just seeing where did that page go. Here it is. Okay. Sorry, folks. Here is again, I'm sharing the screen. I shared my LinkedIn profile earlier by mistake. But okay, here you go. Yeah, and then we extend this.
Bingo. Yes, go to full size.
Yes, we are.
That arrow. Yeah, that arrow. Yeah, that's enough.
Okay, let's start this today. Okay, we are talking about V model in Ultra HDI PCB design. and its challenges, its benefits, and so on and so forth. So today we are talking about 3.0. So you can take it from there.
Yeah, today we are likely to cover the left arm of V. We
Left
start
arm of V. Okay.
with the system specification and come downwards. When you meet the bottom of V, that is actual implementation point. And then on the right side of V, we say how to validate and how to conformity to standards and testing. So this we covered even in our last talk. Basically, the idea is the process nodes are they were decreasing on silicon, but after some time they stopped reducing process nodes because it was not giving enough bang for the buck. Okay, so now that's why people are more than monolithic chip fabrication integration. People are going towards what is called as chiplets, which we told earlier. You put
Yes.
different blocks in a package and try to interconnect them, and it gives a lot of versatility, and the blocks can be reused, but it's got its own challenges. So basically, sometimes we may have to put two different process nodes on the
Mm.
same physical package. So there are various methods of doing it. So, and likewise, when we talk of Ultra HDI, we have already mentioned it is almost going towards at least, if not like a chip design, it's almost like a OSAT RDL layer design. Those kind of design rules are coming into play. The PCB rules will no longer apply. They have,
Mhm.
they have lost their you cannot do it in a negative fabrication. You have to do everything in additive fabrication. So that's why
Additive.
I wanted to just mention this. Again, we had a route map for FCBGA, which was 1990 state of the art. Now it is so many microns, a bump pitch, uh, and a micro via 50 microns, almost diameter, and almost you can see it's not, it's reducing, but not that fast. It's
Mm.
almost 40 in 2022, and 2025 it is 30 microns, and it is going to stay for some time like that, because that is where the heterogeneous integration is playing a major role. You can do more and more with previous technologies. So that's where the investment is now. Again, chiplets are there. There that is available as an IP also. It can be used. And chiplet 2.5D and 3D. When we say 2.5D, it's some sort of a organic interposers will be there. But in 3D, we put one chip above the other chip. We go through the via connection. It is almost like a, whether you are building a large house or you're building a multi-story structure. That is the difference between 2.5D and 3D, roughly telling in a very rough way. But last week, I mean, people are aware that HBM4 is the state of the art. In fact, CAST have published the physical integration mapping up to
Mm.
HBM8. I
Yeah.
mean, it is available up to that level now. Already people are future ready, are future
Yes.
prepared. Okay. So that's how it is. Let's go to the next slide. The challenges, this is not a working model. This is just a schematic representation of how
Mm.
it looks like. We can see here also the via sizes on the chiplet is much smaller and the pitches are much lesser. But when compared to the pitches on the redistribution layer. But finally, this
Correct.
will get aligned in a PCB. Your PCB can still have a zero point 0.8 millimeter bump pitch. So the challenges will come where the signals will fan out to the bump pitch and in fan out region, the what we call as a breakout region. There it is very difficult So you're almost bringing semiconductor technologies and process weights towards a PCB kind of a process width. So that's where the things change. So the high speed, uh, all high speed protocols have to be met. High speed IO on substrate, signal loss, electrical properties, body size, body cannot be wider. Large capacity data processing, multi-core on die. Nowadays we are talking of 1.6 TB worth of a payload on a chip transactions at a data center. That is possible only because of chiplets and heterogeneous integration. That is where even heterogeneous integration is starts where your ultra high density stops. For example, PCB stops at some time, the technology, then it will become high density interconnect, which is also reaching a some sort of a maturity. And then it is gets into ultra high density type of architecture. And then it goes towards chiplets. So that is where
Mhm.
the point is. Again, low power consumption, narrow pitch for bump pitch scaling, high density interconnect. Go to next slide, please. This is again, war page will be there because if the body size comes, there will be a war page. Then you have to use war page control by a proper layout or using a very compliant material. CT mismatch, because there is a multi-layer structure, two different layers will have a different CTE. The CTE mismatch has to be as less as possible. Then you should be able to drill using lasers and fine line width and space fabrication, narrow pitch through hole, signal integration, package design, low decay and DF, almost reaching microwave speeds. Power delivery, more efficient power delivery, embedded multi-layer core, super flat structure, and again, all this will lead into which is this another stream of R&D is happening parallelly.
Mm.
Direct to chip cooling. People want to do liquid cooling directly on the chip package. That's at the data center. That's happening parallelly. So these are all the challenges.
But the question comes here is how you can do the direct cooling on the chip, by the wet cooling system.
Yeah, the coolant is a dielectric basically.
Okay,
The coolant is also dielectric. It's got its own properties, which can be a different topic altogether. But
altogether.
but this is happening only at the hyperscalers and data centers. It is yet to enter, let's say, in-premises server market. They're still air cooled.
Yeah, that is true because
Yeah.
we do read that there are a lot of large data centers is being now built in the US for sure. And also, the cooling system is being one of the major point of discussion. Of course, we will bring that particular topic in one of our future shows. And I'll move on to the next slide now.
Yeah, this is how a chiplet looks. It has got some RF modules and it has got optical modules integrated in a single package. The bumps on the bottom will align with the PCB or in a socket. So finally, the actual PCB becomes just some sort of a carrier where we put all those components, we give power, and even power is given from a backside. That is another topic. No more planar power. It comes directly from the bottom. You imagine you have a 30 layer PCB. On layer 30, you put all decoupling capacitor and the power supply. It drives power directly to layer 1 where the socket is sitting. There is no more planar distribution. It is something like it goes vertically. That is a challenge.
Correct.
So applying V model to Ultra HDI PCB design, uh, I think we have got another 6 more slides. Maybe if you want to take a break now, we can take, or we can take after this slide. Not an
After
issue.
this slide, we'll take it. Yeah, that's what I
Okay.
was thinking. After
So
this.
why we have to apply V model to Ultra HDI PCB design? V model means it doesn't mean that on a CAD package we have a V somewhere and click on that it works automatically. It's not the way. V model should be a company culture. V model should be embedded in your design cycle, in the design flow, and the designers, the supply chain, and the people who do simulation, everybody should follow V model. Otherwise, if one team follows V model, other team doesn't want to, they want to go away from it, it won't work. It should be a company culture. Then only it will work. So applying V model to Ultra HDI PCB design, the V model consists of two arms. Uh, Left is verification, a design verification, and the bottom is actual design, and the right side is the validation. So whatever we do, it has to pass certain international like IEC, IPC, a lot of standards are there, PCI. It has to follow that standards. Otherwise, we cannot sell it in a market. Interoperability becomes a problem. The product cannot be unique. The product has to be interoperable with some other product which is already established in the field or which is going to come in the field, say next year. So that's why it becomes very much important. Left arm, verification and development phase, requirement analysis, system level, very high level system level, focus, define the overall product requirements, including functional block, performance targets, speed, power consumption at a cost. Always now we talk of speed, how much power is required to transfer signals, and there is what is called as a VTF, voltage transfer function. This plays a major role in chip design, and then the cost. It has to be as cheap as possible. Environmental conditions and critical dimensions of Ultra HDI PCB. Ultra HDI specifies. This includes a precise specification of board size, layer count, maximum routing density, signal integrity, impedance control, crosstalk, reflection, thermal dissipation, and manufacturability constraints. We should be able to manufacture. The scale up and scale out becomes a problem. Maybe 10 or 15 PCBs may work, but when we suddenly change from, say, type 15 PCBs to, say, 50 or 100 PCBs, they stop working because the PCB vendor might have shifted it to some other location where they manufacture in bulk. So this is very much important. Okay. And yeah, you have to work with your fabrication partner. They also should be aware. They also should have their own V models, which align with this V model. And a corresponding validation, acceptance testing, unit under test. In fact, the test program starts even before the CAD starts. They all start very
Oh,
simultaneous.
interesting. Mm. So let's take a quick break here and we'll be back again. Good morning, good afternoon, and good evening, and welcome back to Global Electronics Friday Talk Show with your host, Rajiv Kulkarni. Global Electronics Friday Talk Show brings you various topics on electronics manufacturing, whether it can be design related, whether it can be process related, manufacturing, assembly, or logistic, or market trend. So the idea is to bring the wealth of knowledge from the experts in the industry to the people out there in the electronics community. So please do subscribe to the channel so that we can have more viewers in the coming days as well. The more the subscribers, the more the viewers, and that makes our guest happy and that makes us also happy because we are just serving the electronics community. Let's talk about V model and its importance in the Ultra HDI PCB design. And we have been conducting these particular sessions in different parts. So we had session 1, session 2, and today is the session 3, which is also called as 3.0. So we have an expert from our Indian Silicon Valley based technology expert or design expert, Mr. Ambaprasad with us. Ambaprasad carries wealth of experience in design side of electronics industry, and he has been serving the industry for more than 4 decades, and he is the current SMTA president of India chapter. Welcome back, Mr. Ambaprasad, after this small break, and let's continue our discussion. Yep.
Next slide, please. So we have only 4 more slides left. So that gives us enough time to explain it in detail. Or, for example, you were telling Silicon Valley of
Valley.
India, Bangalore.
Yes.
Actually, Silicon Valley is a very old name. Now it is,
Okay.
Bangalore is almost some sort of a go-to place for global capability center. It is a global
Yes,
capability center capital of India. And India
that is
itself is becoming a global capability center, and a lot of designs are coming to Bangalore. And yeah, that has been the case even last whatever 40, 50, 60 years, 70 years. So it has been the case. So okay, let's move with our remodel. System design, it all starts with the system design because whatever we do, we are either retrofitting to a system or we are enhancing a system. The module what we are going to design, when we plug in, it has to seamlessly interoperable and it should enhance the system performance. It starts from there.
yes.
Focus, outline the overall system architecture, define key components, interfaces, power distribution network, and high-level stack-up decisions for Ultra HDI PCB. So when we talk of Ultra HDI, it is 2 plus n plus 2, or 3 plus n plus 3, or 4 plus n plus 4. What you mean by 2 plus n plus 2 is two stacked vias for a fan out, and then the actual routing happens. And that n can be anything. 2 plus n, that n can be maybe 4 layers, 6 layers, 8 layers. And again, 2, it is a mirror image on the other side. This is very important. From center of the PCB, it has to be a mirror image of itself. Otherwise, the warpage will happen. But aerospace, if we do PCBs for aerospace, they won't allow more than 4 layers of a stacked via. They don't approve. So 4 plus n plus 4 is the maximum we can go if we want to cater to a reliability market. Okay. Yeah, of course, people can do something totally different, but
Yeah.
that will be all non-registered, some sort of, a very vagabond kind of designs where they work in their own niche thing. But if you want to follow certain rules, certain standards, you have to follow. So that is 2 plus n plus 2, or 3 plus n plus 3, or 4 plus n plus 4. That is your stack up. Okay.
Correct.
And the stack up, when you do, it has to be shared with the PCB vendor upfront. They should be able to say we are able to fabricate it at their location or a different location of their own factory. So because they have to set up a lot of things. But in spite of all the hype, your Ultra HDI cannot be more than 10 layers. You cannot have something like a 12 or a 16 layer PCB, Ultra HDI. It doesn't make sense. So if you want to go for a 16 layer or something, you can go with a conventional PCB with a back drilling. So that's the sort of assumptions. If you do Ultra HDI at say 12 or 16 layers, that becomes very expensive, and it's very difficult to maintain that. Reliability is a question mark. That's why you stop at say something like a 10 layer or at the maximum 12 layers. So
And
okay,
but I have a
Ultra
question
HDI
here.
specifics. Yeah.
Yeah, I have a question here. When you say
Mm.
stop at 10 layer, but there can be also application related also, right? For example, if they have to do an Ultra HDI more than 12, 16 layers or something like that
Yeah.
for application specifically,
Mm.
if I
Yeah.
consider aerospace or
Yeah. Yeah.
defense application, don't you think they can go with that?
They cannot go actually as on today because they are bound by their own reliability models. They
Okay.
play more focus is on reliability, which we are going to talk on the right side of the V arm. But
Okay.
Ultra HDI with n number of layers, with we do whatever we like to do, sort of a thing. See, there are in a PCB there are two type of let's say errors, and let me call errors. One is a soft error, one is a hard error. Hard error means your PCB is not mechanically feasible to do. It
Hmm.
becomes a little thicker than the envelope or little thinner than the envelope. When it becomes thinner, warpage is more. When it is thicker than the envelope, it won't go get into inside the system. Okay. So
Hmm.
signal integrity is not a problem. Your signal integrity, power integrity to a certain extent, they are soft errors. It can be manipulated. But mechanical integrity, structural integrity, and thermal. This is a hard error. Suddenly it becomes too hard. Imagine you have more number of layers, there are more chances of delamination. The gap between the two layers becomes less. So that's where it
Right.
becomes a problem. So it becomes a multidisciplinary, multi physics simulation. Okay, I have a 12 layer PCB or I have a 10 layer PCB. 10 layer PCB is more robust in the given design space than a 12 layer
Hmm.
PCB. So that's the
Yeah.
assumption.
Okay.
Yeah. Ultra HDI specifics. No, no, just go back. I think you jumped on slide. Okay,
No,
Ultra
no, no.
HDI specifics.
Yeah.
Specific to Ultra HDI, the system architecture.
Yeah.
This involves initial stack-up planning, material selection for high-frequency performance and thermal properties, and high-level planning for critical signal routing. Basically, differential routing and clock. These are supposed to be very critical. High-speed interfaces. Early discussions with manufacturers about the capabilities for Ultra HDI are very crucial step here. Corresponding validation. This will be validated in system testing. Basically, you will be having your digital twin model that will be verified. See, there are two type of test you do. You have a FA, first article analysis. That is the EFA and PFA. EFA
Hmm.
means it is your model. It is
Correct.
electronic model first article, which is also called as a digital twin. And the PFA is the physical model. So your physical model, it has to meet the specific requirements what we projected in the
Hmm.
digital twin. That is the requirement. Next slide, please. Uh,
Left down.
Architectural design, detailed PCB design and subsystems. Focus, break down the system into smaller manageable subblocks. For PCBs, this means defining the layout of a major block, critical component placement, and overall routing strategies. Rajiv, believe me,
Hmm.
even now, there is no intelligence in placement. Placement is done by human beings. The intelligence is there in AI is applicable to routing, trace routing, but not for placement, especially analog placement and RF placement. It is done by experts and it will be validated by some a parallel review will happen or a peer level review will happen. This is a very crucial stage. Ultra HDI specifications for this detailed planning of a microwave structure, stacked or staggered, both are applicable, but don't use stacked as well as staggered in one, that becomes a nightmare. BGA fan out strategies, power and ground plane design, initial placement of fine pitch components, consideration of a thermal via and heat sink. This phase also includes defining interfaces between different sections of a PCB. So there are some protocols are available. It has to follow those paths. So that's okay. That is called as a your breakout region, or in a local language, in a design language, we call as a shoreline. Shoreline
Sure.
means that is
Yeah.
where the your specific interfaces will fan out. Corresponding valent integration testing. So, for example, you are having a socket. The socket can be designed for 112 Gbps kind of an operation, but right now you may be using only half of that. But it is done with a future in mind. So when we do this design, now it may look highly futuristic, but when we do 112 Gbps, it just fits in. That's it. Okay, next page, please. Uh, Module design, component level design and layout, focus, detailed design of individual components and their immediate surroundings, including schematic capture and specific layout and sensitive areas. Ultra HDI specifics in this are fine-tuning trace width and spacing, precise placement of microvias and via and pad structures, length matching for high-speed signals, detailed impedance control and thermal management strategies for individual components. This is where the routing complexities of Ultra HDI are directly addressed. This is where addressing. For example, we may try to do some planning, we may change pin assignment, or we may do a lot of, there will be a lot of to and fro will happen. The corresponding validation is unit testing. When I say corresponding validation, this will be revisited on the right arm of the V. Okay, next page, please.
I
I think
think
that
we
is
are
the end
done.
of it.
Yep.
Go back.
So it is a very interesting
Yeah, just go back
explanation.
to one slide. I mean, you can just back pedal.
Explanation. Yeah.
So what we do is next interaction, we go to the actual bottom of V, where we do the exact design, and there we show, we tick everything, and the left arm, whatever we have addressed, have we done it? Yes. Then we do the actual implementation of design. This can be one session of the class. Then we can go for the right arm of the V. And a very interesting uh, topic I want to say to the audience who are following this
Audience.
channel, and even for the
Mhm.
general design
Yes.
fraternity.
Yes. Yes. Please go ahead.
Now we are talking of AI and ML in simulation and assembly. In fact, the AI and ML for simulation was done in 1990, but that time they didn't call it as AI and ML. They were calling by their own names. But this started in
Terminology.
1990 actually. 1990
Okay.
means some of the leading edge designers of today must have been in their preschools or something. So I
Yes.
mean, that means this is a 30 years of, uh, the kind of R&D has gone into this. Yeah.
Yes. Very interesting. Very interesting. And I think we will have more session on different topics with Mr. Ambaprasad moving forward. And so thank you all for watching today's session. Next week, we will not have any session because next week is July 4th,
Yeah.
which is American Independence Day. And that day we will be off, and we will come back after next week. And so with the different, definitely a topic. And you know, if you are interested in participating, please write to us with the topic, or if you're interested in any particular topic, then we have a speaker like Ambaprasad who can definitely take up those kind of topics, and we can give a live talk show on those topics. So Global Electronics' main purpose here is to serve the electronics community in the electronics manufacturing sector related to any part, whether it's a design, quality, process, production, or manufacturing, assemblies, supply chain or logistic, or the marketing and the trend. There are several topics exist and to be covered. So every week you'll find a different topic. Sometimes you find the same speakers, sometimes you find different speakers. Thank you all for watching, and thank you very much, Mr. Ambaprasad, for joining us today and giving your insight about the V model and its importance in the Ultra HDI PCB design. So happy weekend, and wherever you are, whichever part of the world you are, and God bless and take care of yourself, and we'll meet next time on the same channel at the same time. Thank you all.
Wow.